Alright, so we have talked about the wave function in the position basis, which means that if we have a quantum state psi, we will define a function such that we take the inner product of the quantum state with the position basis, and this gives us a function which we call the wave function. So this wave function and this quantum state are totally equivalent ways of representing quantum reality. Either you can use this wave function or you can use the quantum state. In the former half of the course, we've been using quantum states as objects that live in a Hilbert space. These functions are equivalent descriptions of the same quantum state, which is reality, which is the objective reality that you're observing. This wave function, however, has certain advantages in certain cases. We've also noticed that this object is called the probability density function. Right? We've also noticed that this integral has to be equal to 1 when you integrate over all of space. We also know that if we would like to take the expectation value of any function f, where f is some observable perhaps, then this expectation value will be given by dx f multiplied by the probability density function. This will give us the average value of the observable f. Right? So these are starting points, and we've also learned that if we have a wave function and if we are able to draw this wave function, which means that the wave function is real. Drawing wave functions means that the wave function is real. If the wave function is complex, which in general it is, you have to draw the real and the imaginary part separately. However, if this were the wave function, one thing that you observe is that under this requirement, which is the normalization requirement for the wave function, the area under this curve is 0. Now, if you make a measurement of the position, which is an observable, you generate a new quantum state, right? Because you collapse into one of the eigenstates of the position operator. Suppose your microscope or your detection apparatus measures the position to be x naught. Right? This means you've created a new state x naught. Initially your state was psi, whose wave function is given by this humpy curve, and now you've measured the position, and it turns out that your instrument gives you a position of x naught. Now there is no uncertainty in this value, it's a precise value. This value is only limited by your instrumental uncertainty. You buy a more expensive instrument, this instrumental uncertainty can decrease. But this is purely instrumental. Okay? So you get a precise value of x naught, which means you've generated a new state, because this is one of the postulates of quantum mechanics. And this new state also has a corresponding wave function. This wave function will be the projection of x naught onto the position basis. And we've learned that this is just a Dirac delta function. A function that only exists at x naught and is 0 elsewhere. Alright? So this function only exists at x naught, it goes to infinity here. Everywhere else it's 0. It's a Dirac delta function. So this is something that we've already learned. And this gives physical meaning to the idea of collapse of a wave function. When we make a measurement, we are generating a new wave function. Or we have collapsed the original wave function into a Dirac delta function. We get a new wave function, a new quantum state. Alright? Now if we have an identical object whose original wave function is still the same, because it's quantum mechanically identical to the first object. So we have a long a repetition of identical electrons, all prepared in the same state, coming into our microscope. So it's well nigh possible that once you get a value x naught and you collapse your electron into this state, x naught, it's also possible that in another run of the experiment on a different but identical electron, right? On a different but identical electron you generate this wave function, x naught prime. And yet another electron, different but identical, you generate another quantum state. Now the probability of generating either one of these quantum states is simply given by the original wave quantum state collapsed onto whatever state you're projecting onto modulus squared, right? So you'll get either of these new quantum states and the probability of these respective states will be given by this. Okay? So if you would like to measure what the wave function, the original wave function is, you'll have to repeat the experiment on different but identically prepared particles. Okay? Otherwise you cannot bootstrap and find out what the original quantum state is, because in one run you just collapse your quantum state onto this point. If you would like to find what this function is, you'll have to build a frequency histogram. You'll have to repeat the experiment a large number of times, and what you will get is sometimes you'll get a measurement outcome here. You will put a small rectangle and then you will build up your experiment. Over a large number of experiments, you will build up a histogram. And if you join the tops of these bins, you will generate the wave function. In fact, what you will generate is not the wave function, but its modulus squared. Okay? So you will generate the modulus squared, the probability density, because that's what you're measuring. You're not measuring the wave function. You're measuring the probability density of the wave function. Alright, so this is quantum mechanics at its best. This is what quantum mechanics tells you. And uncertainty means that if you repeat the experiment on an identical preparation of electrons, protons, whatever particles you're talking about, you'll get a spread in the values of x's. This is uncertainty. But in a single shot, you're going to collapse your wave function onto a precise state. And this width of this bin will only depend upon your instrument. But what Heisenberg's principle states is it talks about delta x. And that delta x is the realm of possibilities of x, which you can encounter when you perform the experiment on a large number of identically prepared electrons. Okay? So I hope you understand what is quantum uncertainty. Quantum uncertainty corresponds to this width, this range of possibilities of x that you can measure, that you can potentially collapse your state into in a single measurement. This is a realm of possibilities. रियाल का मतलब एक पूरी रेंज है, मुमकिनात की दुनिया है, पूरी मुमकिनात की दुनिया, उसमें से किसी एक में आपने कोलैप्स करना है वेव फंक्शन. ठीक है? That is quantum uncertainty. That is what is referred to as by delta x. जी.
सर ये जिसकी डेवलपमेंट हुई थी वो स्टैटिस्टिकल मैकेनिक्स से थ्रू है?
नहीं, क्वांटम मैकेनिक्स की डेवलपमेंट जो ब्राउनियन मोशन है, जो क्वांटाइज कर रहा है मोशन को, उसकी डेवलपमेंट हुई स्टैटिस्टिकल मैकेनिक्स के थ्रू, आइंस्टाइन का जो 1905 का पेपर है. लेकिन दिस इज डेवलप्ड इंडिपेंडेंटली ऑफ स्टैटिस्टिकल मैकेनिक्स. इट्स स्टैटिस्टिक्स, not statistical mechanics. In order to build this probability density function, you'll have to look at the statistics of many outcomes. Okay? So this is material in quantum mechanics, standard quantum mechanics you should all be familiar with. And I'll ask plenty of questions to this effect. What is uncertainty? Lots of multiple choices perhaps in the final exam. Okay? So brush up your concepts which probably we've learned from the previous year, and I don't want to repeat all of them over and over again. So now what we've been talking about is representing your quantum states in the position basis. And we get a function in which is a function of x, which is called the wave function. Now, but on equal footing stands the momentum basis. You can choose to measure the momentum of a particle. rather than looking at its position. So P is also an observable. So if I have some quantum state and I choose to measure the momentum, remember we're talking about one-dimensional motion. We choose to measure the momentum, so there is an observable corresponding to the momentum P hat. And suppose our state is given by ket P. Now, this operator acts on this ket P. Suppose this is an eigenstate of the momentum operator. You measured the momentum and you recovered your original state. Okay. Just this is completely analogous to this expression. The position operator acting on its eigenstate. All the position states are eigenstates of the position operator. Likewise, all the possibilities of momentum, which correspond to certain quantum states, are eigenstates of the momentum operator. अगर आपको इस पर यकीन है तो उसी तरीके से आपको इस पर भी यकीन होना चाहिए, कोई फर्क नहीं दोनों स्टेटमेंट्स में. अब एक क्वांटम स्टेट है psi. You can either choose to measure its position or its momentum. You can either choose to represent it in terms of position or in terms of momentum. So if you choose to represent it in terms of position, this is called the wave function. In the position basis, it's a function of x. But you can also choose to measure the same quantum state. Now these quantum states represent the same quantum reality, the same objective reality that you're trying to look at. Okay, there's no difference. It's the same electron. You can either measure its position or its momentum, doesn't matter. It possesses both position and momentum. If you're using a microscope, you can measure its position. If you're doing an interference experiment, you can measure its momentum. Okay? Ji.
Does presenting psi in dx basis draw information about the field?
Yeah, we're going to learn about this, right? Okay? In this class today. So I can choose to represent it in the momentum basis. Now this will give me a function of the momentum. Is this function going to be the same as this function? Not necessarily. So I just try to put a tilde on top of it. So it's the wave function in the momentum basis. Okay. It's not necessarily the same as this wave function. Okay. So we can define if this is real. Suppose this is real. Okay. Suppose this is my wave function in the momentum space. Okay. Now if I choose to measure its momentum, I can get a realm of possibilities. And when I measure its momentum, I get a particular value of the momentum. Let's call it P naught. And when I measure the momentum, I collapse this wave function onto an eigenstate of the momentum. My original state was psi, ket psi. I measured the momentum of the particle, and it turns out that I get P naught. I can get anything depending upon this probability density function, but I get some value, P naught, which means I have created a new state, ket P naught. And if I look at the wave function of this state in the momentum basis, it's going to look like a Dirac delta function. So I create a new wave function which is given by the inner product of P with P naught. This is just a delta function that only exists at P naught and is zero elsewhere. Alright? बिल्कुल analogous है उस particular description.
आज तो ज्यादा जरा में असलहा चाहिए.
बिल्कुल, there's a one-to-one correspondence between these descriptions. Now, if suppose I would like to find the probability that I have a particle whose wave function is given by this form. I want to find the probability that I measure a momentum between P1 and P2. It's just the area under this curve. So the probability that in a single experiment I get a momentum that is in between these values will be given by the integral from P1 to P2 with respect to P of the probability density function, which is now given in the momentum space. Okay, it's completely analogous to the expression that I've written over there. So this is the probability that in a single experiment I get a measurement outcome that's between P1 and P2. ठीक है? बिल्कुल analogous है. All right. Now what would we like to do? And any operator can be represented in any basis. Okay? If I look at this operator x hat, what is operators are represented by matrices? What is the size of this matrix? आप बता सकते हैं कि ये एक ऑपरेटर है ना, x है, ये इसका एक मैट्रिक्स होगा, ठीक है? इसका साइज क्या है इस मैट्रिक्स का? पहले ये बताएं. 2 by 2 है, 3 by 3 है, 4 by 4 है, infinite है, क्योंकि the number of eigenstates is infinite. It's an infinite dimensional Hilbert space. And what are its eigenvalues? They are infinite eigenvalues. And what are the eigenvalues? All real numbers, right? So basically, if I would like to represent this, it's just a diagonal, in its position basis, it's a diagonal matrix whose elements are just the real numbers, all the real numbers. Okay? It's an infinite dimensional matrix. All right. Likewise, if I represent this momentum operator in the momentum basis, right, it's going to be a diagonal matrix with all real values of momentum being possible. The momentum can be plus 1 kilogram meters per second, minus 1 kilogram meters per second, 3 kilogram meters. All the real numbers are possible. Okay? The spectrum, or the spectrum means the list of eigenvalues of this operator, is just the real line, all the real numbers. Okay? But this operator is represented in the momentum basis. I can also represent this operator in the position basis. Now how do I do that? Do you understand the question? What do we want to do? We want to represent the operator P in the position basis. That's what we would like to do. Okay? This is our starting point. Okay? So we know that the translation operator dx acting on the quantum state psi, it creates a new state. Okay? A new state is created whose wave function is translated by dx. Okay? So if this is some new state, phi. If I would like to represent this phi in terms of the wave function, what would I write? I would write dx, the shifted wave function, which is psi x minus dx, cat x, where x goes from minus infinity to plus infinity. I give you half a minute to reflect over this, and if you understand or recall this from the previous ones. This phi is simply dx, phi x. देखो, this new state, quantum state in the Hilbert space is represented as this integral dx, the wave function corresponding to this state, get x. But this wave function is simply the original wave function shifted by dx to the right. Get it? अच्छा. Okay. Now let's look at the right hand side. Dx. Now this shifted wave function, I can write this shifted wave function in the following way. Dx, original wave function, minus derivative of the wave function with respect to x dx x. If I put a dx dash here, x dash, right? I can use any variable I like. I put x dash here. Instead of x, I just replace all the x's by x dashes. Okay, there's no harm in doing that. Now there's a dx dash. I'm integrating with respect to x dash. This is an x dash. Okay. Now this wave function is psi x dash. Derivative of psi x dash with respect to x into dx. Do you understand how I get this term? Okay, you don't. This is just the Taylor expansion. Do you know the Taylor series?
Yes.
Calculus 1 में पढ़ी थी, 2 में पढ़ी थी? 2. Okay. Suppose I have a function of x. Okay. Now this function of x, I can expand this function about any point. Suppose I expand about x naught. What does this mean? This means that I can write this function as function's value at x naught plus x minus x naught into the derivative of f with respect to x computed at x naught plus x minus x naught squared divided by 2 factorial, the double derivative of x with respect to x computed at x naught and so on. This is the Taylor series, the Taylor expansion. Okay, now what does this mean? Let me give you an intuitive idea of what this means. Suppose I have this function, okay, and I have a point x naught. Now this function fx varies with x. What I would like to do, if my x is close to x naught, but it's not at x naught, I would like to find out what is the value of the function close to x naught. Now I can approximate this value, which is really this value, fx, right? This is my x, okay? This is the x that I'm choosing. I would like to find the value of the function here. And this point is close to another point x naught, where I know the value of the function. I don't know the value of the function here. I would like to know the value of the function at a neighboring point. ठीक है? मैं घर में मुझे आपने सारी चीजें पता, लेकिन मैं हमसाए के घर के बारे में कुछ जानना चाहता हूँ, ठीक है? और मुझे पता है कि वो मुझसे ज्यादा अमीर है, उसकी तनख्वाह मेरी तनख्वाह से दुगनी है, ये पता है मुझे अपने घर के हालात पता है, मैं अपने हमसाए के घर के बारे में जानना चाहता हूँ, सिर्फ मुझे फर्क पता है अपना उससे कि उसकी तनख्वाह दुगनी है. So I'm standing at x naught. X naught is my home. I know my own worth at x naught. I would like to find the worth of the function at a neighboring point x. Okay, this is unknown, but I know how different. I know this derivative here, which means I know the gradient from x naught to x. Okay, this is what I know. I can compute the derivative in my home. I can compute the second derivative in my home, the third derivative in my home. So I would like to find out what the value of f is at a neighboring point. So what I do, my first approximation is, alright, if this point is close enough, he's my neighbor, we live in the same locality, he can't be much richer than I am. Okay, so my first zero order approximation is that the value of the function at x is just the value in my home. Okay, so this is the lowest order approximation. Okay. So fx is fx naught, and I ignored higher order terms. The next term is obtained, the correction is obtained by seeing how far away is my neighbor, that is the deviation x minus x naught, and I multiply this by the derivative of the function computed at this point x naught, which simply means that I'm looking at the derivative here, which is just the slope of the line at this point. Okay, so this is the slope. Slope means this length of the triangle divided by this length, and if I multiply this slope with this difference, which means by the base of this triangle, I will get this height. Okay, so if the slope of this line is m, this is delta x, I multiply m by delta x, I will get this delta y. So I will add this delta y to my value at x naught, which is this value, and I will get the next order approximation to fx. Higher order approximations are likewise, because this is not a straight line. The first term just assumes that there's a straight line between this point and this point, but it's a curve. So you have to take the first order derivative, the second order derivative, and so on. This is the meaning of the Taylor series. I give you 1 minute to think about it. So according to the Taylor expansion, this wave function at a neighboring point, given my center point x dash, is given by the wave function at its home value x dash. There is a minus sign here, so I put a minus here. The slope of the function, perhaps computed at x dash, okay, multiplied by how far am I from my home. Okay, so this is just the lowest order term in the Taylor expansion. I will not put this x dash over and over again. Alright, so if I have two terms in the bracket, so the right hand side becomes equal to dx dash psi x dash, right, minus dx dash derivative of psi x dash with respect to x dx x dash, right? Okay. Now what is this equal to? What is the first term equal to? Zen?
Psi of x dash whole square.
Nahin. What is this? It's just equal to psi. Okay. Any quantum state is given by this expression. This is just a wave function. अगर मैं x dash लिखा है कोई फर्क नहीं पड़ता, x double dash लिख लूँ, x triple dash लिख लूँ, x लिख लूँ, doesn't matter. So this is just kept psi. Now this integral is with respect to dx dash. X is a constant, so it can be brought out of the integral. So I can write dx partial x dx dash psi x dash x dash. Now what is this equal to? Get psi. So I have psi minus dx psi. So I have identity minus dx psi, right? This is just an operator. This operator is looking for its operand. ठीक है? ये शिकारी है, आपके शिकार की तलाश में, इसलिए किसी चीज को हड़प करना है, आगे उसको मिलेगी आगे चीज. It's just an operator looking for its operand. Okay? Now this is the right hand side of this expression. The left hand side is given by this. But we're talking up to the lowest order. Here in the Taylor series, we're just talking to the lowest order in the Taylor series. So this is an infinitesimal operator. We can write this operator to its in its lowest order as follows. The left hand side is p dx acting on psi, which is simply identity minus iota p over h bar dx acting on psi. Remember the previous lectures? P is the generator of translations. Okay? Sometimes you put a small x with this because we're talking about momentum along x. Okay? So if I compare the left hand side with the right hand side, I immediately recognize that I px over h bar is simply given by partial x, which means that my px operator is minus iota h bar partial x. A very important result. This is the momentum operator in the position basis. Now this operator will act on some state. If px acts on a quantum state psi, it really means that in the position representation minus iota h bar partial x psi. This is what this expression means. Both sides can take some quantum states on which they can act. And if you would like to find the action of this operator on this quantum state, it's equal to minus iota h bar times the derivative of the quantum state with respect to x. Okay? If I take the inner product of both of these states with x, px psi, it's simply equal to minus iota h bar partial x. Which is equal to minus iota h bar partial x of the wave function in the position space. Okay, remember this is an integral that can be written in this form. If you take the inner product with x, x only interacts with this and it preserves the term only one term. So this is your final result. Anyway, this is extremely important. The momentum operator in the position basis is given by this. ठीक है, अभी मैं आपको आधे मिनट देता हूँ, तो इसको देख लें, समझ लें, फिर हम आगे चलते हैं. ये किससे सॉल्व होता था नेक्स्ट डे आपने Okay. Suppose I have a quantum state psi, okay, psi. I measure the momentum, right? I measure P. There's an infinite number of outputs possible. Suppose I measure the output to be P naught. Okay? With a certain probability I get P naught. So my output state is get P naught. Now I would like to represent this state in the position basis. Okay? Right? Any state can be represented in any basis. Now I have measured the momentum, I have created a new state, ket P naught, which is an eigenstate of the momentum operator. देखो मेरे जुमलों को बड़े ध्यान से सुनना है. I have measured the momentum and observable. It turns out to be P naught, which means I have created a new quantum state, which is an eigenstate of the operator. Now this new quantum state that I have prepared, I would like to represent this in the position basis, which means I would like to find the wave function of this new state that I have prepared as a function of x. So because what I know is that this new wave function that I have prepared, I know its momentum is precise, it's P naught. Okay, at the time I measured, its momentum is precise, P naught, because the momentum eigenstate in the momentum representation is just the Dirac delta function. This is simply the new state that I prepared in the momentum basis. Okay, it's a delta function in the momentum basis because its momentum is precise, precisely known, no uncertainty. But the same state, what about its uncertainty in the position basis? In other words, what I would like to do is, I prepared this state, I would like to suppose, and for this state I would like to measure x. Where is the particle which has been prepared in this momentum eigenstate? Where is the particle? Right? जिस तरह हम polarization वाले experiments करते हैं, spin वाले experiments करते हैं. Now I'm first measuring the momentum, then I'm measuring the position. So if I would like to find the eigenstates, I would like to represent this state in terms of the position basis elements, right? अगर ये Sx होता, ये Sy होता, Sx की eigenstate मिलती है, उसको फिर Sy की eigenstates की term में represent करते हैं. ठीक है? So I would like to represent this new state that I prepared in the position basis, which means that I would like to find out what P naught x is. What is this wave function in the position basis? सवाल समझ आया? Without the question can't proceed, man. आपको? Okay. Now, okay, let's proceed. We know that the momentum operator P acting on its eigenstate P naught gives me an eigenvalue P naught. Now what I would like to do, I would like to project both of these sides onto the position basis. X, P, P naught. Now this is just a number. P naught is just a number. It's an eigenvalue. So P naught, X, P naught. Okay? And this is something we would actually like to find. ये हमारा unknown है. Because this is the wave function of the momentum eigenstate in the position basis. Right? So x, bra x, p naught, ये किस चीज का फंक्शन होगा? x का कि p का? x का. ठीक है? x का फंक्शन होगा. और मैं छोटा सा p naught लिख लेता हूं क्योंकि I have prepared the state p naught. I have gotten the eigenvalue p naught. So it's really a function of x. When my momentum is precise at p naught. Okay? It's a function of x. Now the right hand side simply becomes p naught, this number, this shear number, this scalar, into this function x. Okay? The left hand side, which is x momentum operator p acting on p naught x. Now this momentum operator is given by minus iota h bar partial x p naught. Okay. Now this bra, this is a number, this is an operator, this bra only interacts with the ket. There's nothing else a bra can do. It can only interact with the ket. So this becomes minus iota h bar partial x p naught. So this is simply the wave function that we would seek to determine. Minus iota h bar partial x wave function. And now what do I have? I equate the left hand side with the right hand side. Minus iota h bar partial x psi p naught x equals p naught psi p naught x. Partial x, the wave function, equals plus iota p naught over h bar partial p naught x. Now can you solve this differential equation? Simple first order differential equation. You can solve it for psi. And the result is, ठीक है सर, इंटीग्रेट इसको इधर ले जाएं, ठीक है, इसको इधर ले जाने के बाद दोनों साइड्स को इंटीग्रेट कर दें, ठीक है, get a natural log which then comes out as the following. The solution turns out as psi p naught x. You have to solve these differential equations on your own. I'm not going to do this in class. So this wave function turns out as c, some constant, e raised to power I p naught x over h bar. I give you 1 minute to just reflect over this, think over it, see what you tell you if you can understand what's going on. Get p naught, which has a precise momentum of p naught. When we represent this state in the position basis, a new quantum state has been prepared. We can represent that quantum state in any basis we like. In the momentum basis, it's precise. You measure the momentum again, right? If you put another measurement operator, which you measure the momentum again, what's the new value of the momentum? It's going to be the same, p naught. You measure the momentum again, it's going to be p naught again. If there is no Hamiltonian, right, the state is not evolving with time. You measure p naught again and again and again and again, you will always get the same outcome. But now what we would like to do is we would like to measure x. So when this state that we made, when we represent this in the position basis, this is the result that we get. Where C is some constant that we will find. However, let's try to draw this wave function. Okay? Now, it's a complex wave function. So we can only draw its real part or its imaginary part or both of them. Okay? So let's draw its real part. X, right? The new wave function is now in the position basis, so my axis is X. And what am I plotting? I am plotting the wave function of the momentum eigenstate, the new state P naught that has been created, as a function of position. Now if I plot just I'm plotting the real part of it, by the way. So the real part is just cosine P naught X over H. So it's going to be a function like this. Whose height is C. This is 0. C is a constant. We'll find out what this constant is. Okay. Now let's think over this function that we plotted. Does this function start somewhere or end somewhere? No, it's eternal. Its expanse is the entire real line. So we precisely know its momentum. But when we plot the momentum eigenstate in the position basis, we have collapsed the momentum, but it turns out that the position is this particle. If you try to look at this particle in a microscope, subsequent to the momentum measurement, it can be anywhere in the world. It can be at minus infinity, plus 5 centimeter, plus 300 kilometers. It can be anywhere. Okay. It's an ideal particle, by the way. So it's delocalized in position. It's localized in momentum, precise in momentum, but totally delocalized in position. If you would like to find out, okay, if you would like to plot the imaginary part, it's just going to be a sine function. It's going to look like this, right? Just going to be a sine function. If you were to plot the probability density, what's the probability density of this function? You take the modulus squared, it's just going to be constant in all of space. If I plot psi P naught X, complex conjugate, multiplied by psi P naught X, which is simply the probability density, it's simply going to be equal to C squared, which is a constant. Agreed? Complex conjugate खुद से multiply होके 1 दे देगा. So the answer is just a constant in space. So if I would like to draw this constant, it's a constant line of height C square, whatever C is. But the point is that it's uniform. So there is uniform probability of finding this particle anywhere in space. We've localized it in momentum, but it's totally delocalized in position. It can be found anywhere. This is uncertainty principle at its best. You precisely know the momentum. There is no uncertainty in the momentum. There has to be infinite uncertainty in the position, which means that if you measure the position of this particle, the realm of possibilities is infinite. You can get any position whatsoever from minus infinity to plus infinity. only then would the uncertainty principle be satisfied. एक मिनट जरा देख लें इसको, आगे पे चलते हैं। आपको देखो, the realm of possibilities is infinite. X can be anywhere.
वो तो उसके अंदर भी है।
किसके अंदर? इसके अंदर? हाँ, क्योंकि एक ही चीज है, इसका मॉड्यूलर स्क्वायर ले लिया ताकि आपको बस रियल मीनिंगफुल एक पिक्चर आए। This is just a wave function. Probability amplitude, you need the probability density. This is real, this is what you measure, this is what your experiments tell you. The experiments don't tell you this, they tell you this. Okay, that's why I have plotted this. Likewise, if I measure the position first, I get x naught. And then if I measure the momentum, there's an infinite possibilities of momentums. X and p are conjugate variables. And we know from the uncertainty principle that delta x multiplied by delta p has to be greater than or equal to h bar over 2. हमने पिछले लेक्चर में ये देखा। अच्छा, एक इंटरेस्टिंग चीज, look at this function which is plotted here. Doesn't it look like what is called a wave, right? Inverted commas में लिख रहा हूँ wave, क्योंकि inverted commas भी होना चाहिए, ठीक है? ये wave की तौर पे लग रहा है, ठीक है? If I look at any 2 points, this is defined as the wavelength lambda. Okay? Right? The distance in the position between 2 points that are in phase is called the wavelength lambda. So if I look at this exponent, when this difference between 2 points is equal to lambda, what is the phase difference? What is the phase difference between these points?
2 pi. 2 pi.
2 pi, which means P naught lambda over h bar is 2 pi. Correct? Now this means lambda equals 2 pi h bar over P naught. This is 2 pi h over 2 pi over P naught, which means lambda equals h over P naught. What is this? The de Broglie relationship. Now this wave that has been created, this wave has a wavelength, everything in inverted commas. It's not a real wave, it's a quantum wave. That's why it's called a wave function. This function is called a wave function because of the reason that I'm explaining. इस सब लफ्जों की हेर फेर है, लफ्जों में ज़्यादा मतलब में घुसना नहीं कि वेव है तो बाकी कोई वेव है, like water wave or waves on a string or on a rope or sound wave. It's a quantum wave. This wave on its own doesn't have any significance. The probability density that shows up. So this so-called wave has a wave function which is given by h, the Planck's constant, divided by the momentum that you've measured. And when you measure the momentum, you get a precise value of momentum. There, the object is behaving like a particle. When the object is behaving like a particle, you created a new state. And in the other conjugate variable, it behaves like a wave. And an object cannot behave like a particle and a wave at the same time, in the same basis. So this is a wave, this is a quantum wave whose wavelength satisfies the de Broglie relationship. The momentum that you have measured, this particle will have a definite momentum because you've measured it, P naught. And the wave associated with this particle in the position space has a wavelength equal to h over P naught. This is what the de Broglie relationship means. चलते हैं, आधे मिनट में आगे चलते हैं। The next question is, how do we find C? Alright. Suppose we have prepared this state P naught. Okay. In the momentum state basis, what is this wave function? Delta P minus P naught. Okay. Correct? But this ket P, P naught is also equal to ket P identity P naught. देखो, wave function in the momentum basis is a Dirac delta function. This is the wave function of P naught in the momentum basis, right? This is the same quantum state P naught, but now represented in the momentum basis. It's a Dirac delta function. It's a different function. I put a tilde on top of it, but it represents the same quantum reality, ket P naught. Now this ket P naught equals the Dirac delta function. We also know that this inner product must be equal to this. Since this is the identity operator, I can write this as dx. P लिख लूँ x फर्क नहीं पड़ेगा, ठीक है? Ket P naught. Because the identity operator, this forms a basis. So I come here equals bra P x P naught dx over all of x. Dx over all of x. Now what is P naught x? What is this state? We've already found this state. C E plus I P naught x over h bar. Right? This is what we found. ये वाली state दरअसल यही तो हमने मालूम की है. Right? This is this state. This is this wave function. ये चीज मैं उठा के इधर ले आया इसकी जगह. Likewise, this is the wave function but the complex conjugate. Okay, so I write C star E minus I but with a P instead of a P naught. P x over h bar. This equals C modulus squared. It's a constant, I can take it out. It can be a complex number, doesn't matter. Dx E I P naught minus P x over h bar. Now this must equal this. This must equal this. ये दोनों बराबर होने चाहिए. Equal. Okay. Now how do I find this integral? This is the integral that I would like to find. So here we use the Fourier transforms, which probably you've already seen in the integrals. I'm sure you have. The 15 students who came to class, I'm sure they've seen it. Fourier transforms. If I have a function psi of x, some function that lives in position space, I can find its Fourier transform, which is defined as the following: E minus I px over h bar integrate over x divided by 1 over 2 pi h bar. This gives me a new function. Since I'm integrating with respect to x, my new function does not have any x in it. It's a function of this momentum p. Okay? This is a new function which is a function of p. Its new function, I put tilde on top of it. This is the definition of the Fourier transform. Don't be frightened if you're not physicists or mathematicians or engineers. This is something very easy. If you know integration, you can always solve this. ठीक है? परेशान नहीं होना. थोड़ी सी प्रैक्टिस करोगे, मेरे पास आओ, मैं करवा दूंगा. It's easy. Okay? So this is the definition of Fourier transform. यूँ समझो कि एक फंक्शन है जो पोजीशन की मुल्क में रहता है, उसकी करेंसी पोजीशन है, वो पोजीशन की करेंसी में लेन देन का कारोबार होता है. जो भी वो सरहद पार करके दूसरे मुल्क में जाता है, it makes transactions in the momentum currency. Right? So you can represent a function in the position basis. If you take its Fourier transform, you go to the momentum space. The same function is now represented in the momentum space. The function has a different shape, right? But it represents the same quantum reality. So you can represent functions in position or momentum. Likewise, you can do an inverse operation. You can find the inverse Fourier transform. So this is sometimes called the direct Fourier transform of psi x, which means you take the Fourier transform of psi x and your result is function of p. Right? So this is defined as the direct Fourier transform. Likewise, you can start off with this and recover this if you do an inverse Fourier transform. The inverse Fourier transform is this: you have this function of p, you integrate with respect to p, e with a plus sign here, I px over h bar divide by 1 over 2 pi h bar, and you get the function in the position space. Which means if you take the inverse Fourier transform of this, you will get this, represented as the inverse Fourier transform of the wave function in the momentum space gives me the wave function in the position space. So these are two definitions. So you can write these down. अब हम इनको इस्तेमाल करके we would like to find out this integral, so that we can find out what C is. And then we'll finish in 10 minutes. Okay, so don't worry, we're not going to go overboard. Now let's look at this definition. Psi of P equals 1 over 2 pi h bar dx psi x, the wave function, E minus I px over h bar. Okay. Now this wave function in the position space can also be written in this form. Right? So I take this definition of the wave function and bring it here. Okay? 1 over 2 pi h bar dx. Now this wave function, I replace it with the inverse Fourier transform. So I'm putting everything in big brackets. 1 over 2 pi h bar. Now I use a different variable. I don't use dp, I use p dash because there is already a p here. So I use a dp dash. Changing p to p dash doesn't really matter. Just a change of variable. Psi tilde p dash e plus I p dash x over h bar, and then I put this bracket again, e minus I p x over h bar. Okay. Now this is an integration with respect to x. This is an integration with respect to p dash. I can do this integration first or this integration, it doesn't really matter. So what I would like to do, I would like to take this constant out so that it stops getting on my nerves. 2 pi h bar. I move this integral out. So this is an integral with respect to p dash, this is an integral with respect to x. I bring this integral out, I get p dash dp dash psi tilde p dash dx. Now I have to introduce the dx integral because the terms that I am going to write have an x in them. Plus I p dash minus p x over h bar. Alright? This is with respect to x. Alright? This is with respect to x. चलूं आगे. All right. But what is this equal to? All of this must be equal to psi p psi tilde p, right? This is what we started off from. Okay. Now, if all of this must be equal to this, which occurs here, what should this be equal to? Unity. Okay. Now, there is a property of Dirac delta functions. वहां तक आप जितनी देर में मिटाता हूं वो देखें कि उसकी समझ आएगी उन सब स्टेप्स की. Function of y, some function of y, you're integrating with respect to y. Okay? If you have delta y minus y naught and you're integrating with respect to y from minus infinity to plus infinity. Okay? Suppose you have a situation like this. Inside the integral there is some function of y and you multiply that function by the Dirac delta function which is non-zero only when the argument is 0. So, could you tell me what should be the answer of this? एक वैल्यू कौन सी वैल्यू होगी? f की एक वैल्यू होगी किस पॉइंट पर? y0 पर. So this integral equals the value of the function at y0. Okay. This is called the sampling. This is sampling. You are sampling the function at the only one point, the point where the Dirac delta function is non-zero. Okay. So if you would like to make this equal to psi at p, all of this, and you have a psi at p dash, what should this be equal to?
Delta of P.
Delta
P.
p p dash minus p, right? If this is delta at p dash minus p, then you're only picking one value of p dash, which is p, and you'll get this back here. But remember, there's a 2 pi h here as well. So this thing that I've written in blue brackets, this thing must be equal to 2 pi h bar delta p dash has to be equal to p. Okay. So what is this now? This is simply the same integral that we've written with the p naught replaced by p dash. So this must equal, this thing must equal 2 pi h bar delta of p naught minus p.
I don't get that must equal that. Dirac measurement.
ये समझ रहे हैं?
जी सर.
तो देखो ना, बिल्कुल यही उसूल यहाँ हम लागू करते हैं. If you have something here, you need a function here, some function here, so that overall this equals this function computed sampled at a single point p. Okay? Suppose this is your f of y, right? You want to have y equals y naught, because you have a y naught here. So what you would like to do, you will have like a Dirac delta function which is y minus y naught. So you just put all of this equal to this function, so that you are sampling only the value of p dash which equals p. So this must equal this. Hence, this factor is 2 pi h bar delta p naught minus p. So my c mod square 2 pi h bar delta p naught minus p must equal delta p naught minus p. This means that my c must equal 1 over 2 pi h bar under root. This possibility, right? Can have a global phase as well, but that doesn't matter. So my momentum eigenstate in the position basis is simply 1 over 2 pi h bar under root e I p naught x over h bar. I have found out the constant c. This is my momentum eigenstate in the position basis. And this momentum eigenstate in the position basis, right? The same quantum state in the momentum basis. It's delta p minus p naught or p naught minus p, doesn't matter. Okay. Now I'll give you more description of the Fourier transform on Monday. What does the Fourier transform really mean? But this is one working example of using the Fourier transform. If you get a wave function in the position space, you want to find the corresponding wave function in the momentum space, take the Fourier transform. If you have the wave function in the momentum space, you want to find the wave function of the same quantum state in the position, take the inverse Fourier transform. Okay? So the Fourier transform lets you go from the positions representation to the momentum representation. Okay? And as a homework, something that you've done in the tutorial, take a function in x, right, which is a height a, goes from say minus b to plus b. This is your function psi x. Suppose this is some hypothetical function, wave function. Find the Fourier transform of this. Use your definition and find the Fourier transform of this. You should get a sinc function. Right? And I'll explain more on this on Monday. So the plan is that I think we have 4 more lectures. 3 more lectures. 30th May को नहीं lecture. वो भी तो है.
29th आखिरी
29th आखिरी हम कर लेंगे 30th को 29th को कर लेंगे. क्योंकि what we would like to cover is the Schrödinger equation in the position representation, infinite well, tunneling. Only one lecture because you've already seen that material. Okay? We'll go lightning fast through it. Then we'll have 2 lectures on the hydrogen atom. And then we'll finish it. 1 more homework and 1 more quiz. Okay? And I'm going to, your final exam will have a good number of multiple choice questions as well. So brush up your concepts. No slacking on the concepts. And you have to have refined sense of mathematics as well. Okay? So inshallah see you next week.